do a little bit of revision on Markov chains for this section. Now, the reason I'm doing this is because you only just touched on Markov chains, and Markov chains is a really in-depth subject, and it's actually really quite important one for a lot of client cases. And it actually, like I say, it does come up more in the quantitative finance, and it is particularly useful in doing things like pricing stock options. And so it is sort of one of those things where you should know. But because you guys only just touch on it, a lot of the other stuff we do that talks about Markov chains is going well beyond what you know, and it also uses techniques which you are not familiar with. So it's not as useful for you to just go, oh, I can do that, I can look over these other ones. So that's why I thought it would be a good idea to sort of talk about how you do Markov chains and how you would be expected to solve them, find the important things. So what is a Markov chain? Markov chain is basically trying to model a process that repeats. So you look at stock pricing, the whole stock market day in, day out does the same sort of things. And without any extra information, the probabilities remain the same. All right, the probability of transitioning from one place to another remains effectively the same. So, and there is movement. So some of the stock market movement is sort of movement for the sake of movement. Brokers make money by buying or selling shares. They don't make money by owning shares. You make money by owning shares. All right. So it is in brokers' interest to move shares. So from that point of view, now I'm going to go and grab the little few notes that I made on this. So the first thing we're going to talk about is the transition matrix. So we have several states. So it's important to know it's a random process. We don't know where it's going to go. All we can say is work out where the probabilities are going, all right? If we could know this, then people would have done that, and then there would be no point of having a stock market because you couldn't be speculative. There would be a deterministic answer, all right? It's a bit like going to the casino and going, yes, well, I can count cards. I made the mistake of telling the security people at the casino that if I was going to gamble, I'd be counting cards. And they're going, yeah, okay. Got your picture, it's all good. So the answer is I don't gamble. So what we're going to do is we're going to create a transition matrix. So we're starting with the transition probabilities. So Pij is the probability so the probability of moving from state I to state J. Now, because these things are a probability, the total probabilities must sum to 1. So, and because that first number, so because this I, which represents the row number, so I, row number, so my sum from j is equal to 1 to n of Pij is got to be equal to 1. Alright? So if I sum along the row, will be equal to 1. this is making the row vectors are probability vectors. So my row vectors are probability vectors for this situation. Yeah? So what this means is if I have a state vector, each of these numbers represents the probability or the proportion in a particular state. So where your xi is so this thing here represents, so a state vector has all these things which are just your probabilities or your proportion of things in that state. Again, it's a probability vector. So again, it's the sum of my xi's, so that means the sum of my xi's is going to be equal to 1. Alright, so this is sort of the basic information. Alright, now, so if x naught is the x1 is equal to x naught times p. So this p and p, whoops. So my P is called my transition matrix, okay? So typical things that you're going to actually be asked to do in the exam are going to be to take the information that's given in the question and create your transition matrix. So it's important to actually sort of know where you're going with that, all right? And the other thing you're going to do is you're going to be told some information about, so there are two things that we do with it once we've got it. One is, given this state, what is the next state, and what is sort of some subsequent state. All right? The other thing we do is we calculate a steady state vector. All right? So the thing about Markov processes is, under certain conditions, you will reach what we call a steady state vector. And that is where the probabilities remain the same. So I'm just going to put in the theory bit first, okay, so that we've talked about it. If P is regular, do we know what regular means? Yeah, that's what I thought. Nobody has any idea. Neither did I. I'd never actually heard this particular piece of information before, but in terms of higher order systems, it's actually important that we qualify that our matrix must be regular. All right? Regular, then so I'm actually paraphrasing your notes. So there's a vector so it's important that P be regular so that you will get a steady state vector. Okay. If P is not regular, the things that the situation is more complicated, and we can say something about steady state, but like I say, there is a whole lot of stuff that happens with Markov chains, and you are really just scratching the surface so that you've heard of them. You have some idea what they're talking about when they come up. Okay, regular. So regular is some power of P has all positive entries. So we're going to have to pause momentarily for a second here and go, P is a probability, is a transition matrix, so every term inside of P is a probability. That means it lies between 0 and 1. All right? Now typically when we construct a transition matrix, we get some zeros in there. All right? Some people don't go from this to that. People don't go from Queensland to South Australia. Just don't know. People don't want to go that way. People do go from South Australia to Queensland. They go from South Australia to pretty much anywhere else. But they don't necessarily come back to South Australia. Sometimes they go to Victoria and go, ooh, well, when it's wet and miserable, and if I'm going to be down to where I might as well be back now. So my transition matrix will quite often have zeros. But when we're saying it's regular, what we're saying is there is some power of it, so there is actually no zeros in the entire of that matrix. All right? So because, like I say, my probabilities, because they're all probabilities, they're all greater than 0, greater than or equal to 0, they're all less than or equal to 1, and so I have to have all non-zero entries in there. And it can actually be a little bit difficult to find. One of the things I recommend if you're asked to show a matrix is regular is to just calculate the first couple of powers and see if any of those have non-zero entries. All right. The other thing is if you calculate the first couple of powers, p squared, p cubed, you might see a pattern. And if that pattern repeats over a couple of terms, then you can pretty much assume it's going to repeat all the way through. So that's one of those things where you need to be aware of that particular trick. All right, so I'm just going to put a number up the top here. I'm going to call that 10 because I forgot what the last number was. So what I'm going to do, so that's the theory part of it, yep. Let's go and see if we can't find an actual exam question so that we can talk about what they actually want you to do with this information. So ideally I'm using 2013 exam for these questions so that we can, a lot of people like to use the exam for their revision and I don't want to do stuff. A lot of people like to save the most recent one for the one they prepare and do just to make sure they're on track. Because that's the one that's going to be most relevant. And let's see if we've got something to actually... And you'd think if I had a plan... Wait! Okay, sweet. That is good enough to read on the screen, isn't it there? Yep. So a phone company offers its customers two plans, Plan X and Plan Y. Customers can only switch plans at the end of the year. All right, the probability that a customer on Plan X will stay on Plan X next year is 0.8. So again, sticking with my theory of trying to do this on separate pieces of paper, mostly so that I can actually scan this stuff through. So this is question 3 from the probability section of the 2013 exam. It's just in case people are listening to it. So what we do? Question 3, prob 2013. So write the transition matrix for this system. All right. So reading through them. So what we're going to do is we need to pick out the information as we go through. All right. So some of it will be explicit. So we said the probability that a customer on Plan X will stay on Plan X is 0.8. Oh no. So we're going to make it quite clear that my being on plan X is my state 1, being on plan Y is my state 2. And so this is saying the probability of going from 1 to 1 is going to be equal to 0.8. And then it says next year is 0.8, while the probability they switch to plan Y is equal to probability of starting on plan 1 and going to plan 2 is going to be equal to 0.2. All right. Now, quite often this other piece of information here is not actually explicitly stated. But because we know the total probability has got to be 1, we can imply that it's going to be 0.2. Okay? We can go, hey, that sum has got to be. So we should be aware that sometimes they won't give us every probability. We might need to calculate them from the information given. So probability of starting in state 2. The probability that the customer on plan Y will stay on plan Y next year is 0.7. So the probability they start at 2 and stay at 2 is 0.7. If I was really smart, I would have put that here, not here, but I didn't. Probability they start at 2 and go to 1 is therefore 0.3, and that bears out. Awesome. So, because I wasn't clever enough about how I've done this, my transition matrix P is going to be 0.8, 0.2, 0.7, and 0.3. All right. I'm going to stop at this point and check. So check row sum R1. So 0.8 plus 0.2 is equal to 1, check. 0.3 plus 0.7 equal to 1, check. Sweet. I haven't stuffed up yet. Okay, so write out the transition matrix for this system. Done. Alright, that's my P. I'm done. How easy was that? 2 marks. Piece of cake. I love it. So, next on my list. Oh. Initially there are 1,000 customers on plan X and 600 on plan Y. So my X naught, so state 1, state 2, and so this is going to be, so there is 1,000 customers on state 1 in plan 1, plan X, and there is 600 on plan Y, and so my initial vector is 1,600. Find how many customers are on each plan 1 year. Assume that no new customers join. Okay, so this is nice and simple. So I'm actually wanting to find, they're asking me to find X1. All right? At Christmas, everyone has a choice whether they stay on their current plan or switch, and they have to decide by New Year. So we're talking New Year's Day. We want to know how many people have switched and how many people are stuck. So I've got my 1,000, got 600, got my matrix, 0.8, 0.2, 0.7, 0.3. You know I was going to do that, didn't you? Okay. So across the row, down the column. So 1,000 times by 0.8 plus 600 times by 0.3. 1,000, whoops, that doesn't weigh, that's not. 1,000 times by 0.2 plus 600 times by 0.7, which is going to be 800 plus 0.3 times 600 is going to be 60 times 3, which is 180. That's one element. And the other one, 200 plus 60 times, so it's going to be plus 420. And so here, this is going to be equal to 980, and this one here is going to be 620. Okay, so here I had 1,600 people. We had no new people, we had no people dropping out. Or maybe the number of new people and the number of the new people took over the old people's plan. Who knows? Check. I add these two numbers up, I get 1600. I haven't made a mistake. And trust me, when it's me doing it, checking is really important, okay? Doing little things to check. And if you do that, all right? Check. Same number of plans in t is equal to 0 to t is equal to 1. So time is equal to 0 to time is equal to 1. Okay? So if we do something like that to check, we should write it down, all right? The little thing that, and the other thing to do is if we do a check and we go it's wrong, we should go, ooh, did this check, it's wrong, I've stuffed up, all right? Don't try and convince the lecturer that you haven't made a mistake when you know you've made a mistake. The lecturer is the smart one, they will know. And I usually find it very amusing when I'm marking exams to find people trying to convince me otherwise, but it doesn't work. I suppose I can say, quite safely say. Now, so this is just modelling that transition. So we see that there's a bit of shift, a bit of drift away from state 1 to state 2, or away from plan X to plan Y. Plan X must be the one that looks good on paper, but plan Y is the one that people find is what they actually use. You know, you go, hey, I want that 10 gig plan, because I really love using my data, but then you go, actually, no, I really only use 4 gig a month, so I might as well drop down a plan. Or vice versa. Find the steady state vector. So this is your bog standard Markov chain question. Write out the transition matrix, given a particular state, find the next state, or find a state thereafter. Give me the steady state vector. The steady state vector is the thing that says, hey, what is my distribution going to be like? Now, so I'm going to go V is equal to V1, V2, all right? And so we're making V as, so this is no longer a number of people, this is going to be a proportion of people, all right? So we've got V1 plus V2 is equal to, I'm going to make that equal to 1, because it's a probability vector. Total proportion of people have got to be this, so therefore possibly, I'm going to come back and talk about part B again in a different way. So, if I have V1, V2 is equal to V1, V2 by 0.8, 0.2, 0.3, 0.7, then that first component, this V1, is going to be equal to V1 times 0.8. It's going to be equal to 0.8 V1 plus 0.3 V2. Okay, so what I'm going to do is I'm going to rearrange this equation. I'm going to put this over here. So I'm going to have V1 minus 0.8 V1 is equal to 0.3 V2, or 0.2 V1 is equal to 0.3 V2. And so V1 is equal to 0.3 on 0.2 times by V2. 1.5 V2. Oh, sorry. Really sorry about that. That's the end of the page. This second component, V2, is going to be, so this is where I go, is equal to 0.2 V1 plus 0.7 V2. So what I'm going to do is V1 is a 1.5 V2, and so this is going to be 0.3 V2. Conveniently, I've got 0.2 V1 here, is equal to 0.3 V2, so I'm going to go plus 0.7 V2. Damn, wrong way. What did I just do? Alright. This system is such that if I just do this other equation, use this thing from the first one and put it into the second one, I'm going to get that. It's going to tell me that V2 is equal to V2. And that's a good thing, because it says I didn't make a mistake. If I do that and I go, ooh, I get V2 is equal to half V2, maybe I've made a mistake. So what I have to do is I have to take this relationship and put it back into this thing. I know that this thing is a probability vector. And so because V1 is equal to 1.5 V2, I go 1.5 V2 plus V2 is going to be equal to 1. So this is 2.5 V2 is going to be equal to 1. So therefore, V2 is going to be equal to 1 divided by 2.5. And 1 divided by 2.5 is going to be 0.4. 2.5 is equal to 5 on 2. So this is going to be equal to 2 on 5, which is equal to 0.4. And therefore, B1 is equal to 0.6. All right. So point 6, 0.4. All right. So that's saying 60% of my customers are on plan X and 40% are on plan Y. And if I'm talking about 1,600 people, so 0.6 times by 1,600 on plan X. This is actually, you don't actually need to do this for the question, but just to illustrate what's going on. And 6 times by 16 is the same as 8 times by 12, which is like 1,080. That seems a bit bigger than I was expecting. But anyway, I'm going to ignore that detail. And ask myself, did I make a mistake in doing that? 6 times by 160 should be the same as 12 times by 80. Oh, 96. 960. Sweet, good, much happier with that number. And so 0.4 times by 16 on plan Y would be equal to 640. Those numbers make me a lot happier. Okay, so that's how so this is my steady state vector. It's a probability vector. So what I'm going to do is I'm going to just spend like just another couple of minutes talking about how I do, how I talk about doing part B as a probability vector rather than a number of people. So we saw how in part B we had x naught was 1,600. What we really want to do is we ideally want to write that as a probability vector. So I'm going to x naught dashed. So we're going to transform this into a probability vector, and that's going to get me 1,000 on 1,600 and 600 on 1,600. So I'm going to get rid of my zeros. First thing we should always do is get rid of zeros because they suck. And this is going to get me 5 on 8 and 3 on 8, which is equal to, I'm going to go with 0.625 and 0.375. Okay, so if I'd done that with this, my x1 prime would be equal to 0.625 times by, and 0.375 times by, and then the 0.8, 0.2, 0.3, 0.7. This number is going to be a whole, I'm going to revert back to the fractional form because it's going to be a whole lot easier to work out. So it's going to be 0.8, so I'm going to write that as 8 on 10 times by 5 on 8 plus that times that, so my 3 on 8 times by 3 on 10. Alright, sure. Yep. And my other component is going to be 5 on 8 times by 2 on 10 plus 3 on 8 times by 7 on 10. And so, let's do some cancelling. That's going to get me a 2, and so that's going to cancel out altogether. Really? So my 5 cancels here with a 2, and my 8 cancels here. And so I'm left with 1 on 2 plus 9 on 80. Scrap that plan. What we're going to do is we're going to write this as something on 80. So that's going to be 40 plus 9. And this is going to be 10 plus 21 on 80. So 49 on 80. 31 on 80. Alright. So I could do this as a probability vector as well. Alright? And I'd be in two minds. My initial reaction is you should do it as a probability vector because that's the way it's been discussed about. But you'll see that it was a lot easier to do it in terms of just the proportion of people, this number of people going to this state. All right. If I do these numbers, you'll find that they're exactly the same as this, but it's sort of not so easy to work out. Okay. Any more questions before we close off for the day? Questions? No. All right. Well, remember you can always come and talk to us in the Maths Learning Centre. Please do come and talk to us if you're having difficulties. Yep.
That last thing you did, would you put that instead of 1,600 and then multiply it by 0.8?
This is what I mean by your discussion in lectures, as far as I saw, was in terms of the proportions.
Yeah.
And so I'd probably do it that second way, which is why I went and did it. And it's sort of the way they do Markov chains actually fight some of my natural instincts for doing Markov chains. So yes, I would do it in that second way over the first way, but that first way would still be fine. You just want to convert it back into proportions.
Oh, okay.
All right. So you can do the nice amounts and then convert it into proportions. Because your state vector theoretically is a probability vector, those terms should sum to 1. And clearly 1,600 do not sum to 1. So, yeah. But, like I say, it is sort of, on one hand it's an equivalent way of doing it, on the other hand I don't know how pedantic your lecturer is in wanting a particular way. Alright? Anything else? Alright, well, thank you. You've been most attentive and helpful with your questions. Good luck with the exam, everybody.